So now we're talking about piecewise defined functions, which is part of section 3.4, and this is learning objective number 2. So what is a piecewise defined function? Well, it's a function that has different behavior depending on what x is. Let's look at example 1 to see what I mean. So it says this, given f of x equals, and there's a bracket. So f of x can equal x cubed if x is less than 1, else it equals the absolute value of x if x is greater than or equal to 1. Okay, so let's talk about the questions that follow. Part A says this, graph the function. Okay, so we're going to look at each piece. Y equals x cubed is how it looks if x is less than 1. So I need to put x equals 1 along here. Okay, and so this graph, which I'll make green, is going to look like the cubic function from the library of functions. And that looks like this. So I'm going to have this drawn. Let me fix that. It looks like this. Like that. Okay? So we talked about this one. Now I'm going to go to absolute value, the other piece, if x is greater than or equal to 1. So normally the absolute value graph from the library of functions looks like a V. But I'm not going to have the whole V, because the vertex of that V starts at x equals 0, and I'm not allowed to be the absolute value if I'm to the left of 1. So here's what it's going to be. It's going to be the absolute value graph except to the right of 1 and including 1. So it's going to look like that. And these two graphs meet at the same place, and the reason they meet at the same place is if you were to plug in x equals 1, even though you're not allowed to right now, if you did, you would get that the graph of x cubed is approaching 1 cubed. Okay, so that's why they meet like that. So that's the answer to part A. Next question, find the domain. Well, the domain, as before, means the x values. So you look to see, are there any x values that aren't reached? And the fact remains that there's no problem. So the domain is all real numbers. You're going from negative infinity up to positive infinity. Okay. Next question. Locate any intercepts. Give them as ordered pairs. Well, the only intercept for this function is right here. It crosses the x and y axes right here at the origin. So it's 0, 0. That's the only intercept. Okay. That's the end of that example. Let's go to example 2. So this is the opposite of the previous question. In this problem, let me read it to you. You're given the piecewise defined function. Now you have to come up with the functions that gave that. Okay, so we'll do that. So if you notice, there's two lines. So we're basically going to figure out the two lines. And where they split up is at x equals 0. So whatever we're going to do, we're going to at least say this, that we're going to have to include 0 up here and 0 here. So let's start working on it. Let's look at the line on the left and the line on the right. In both cases, I'm going to have to plug into this formula. Y equals mx plus b. M is the slope, b is the y-intercept. Okay, so let's get the slope of the left-hand line. So slope, remember, is rise over run. So the rise is 2, and the run is negative 3. So that's my slope for the left-hand line. Therefore, my left-hand line is just y equals negative 2/3 of x. Okay? So I'm going to put that in. Y equals, that's already there, negative 2/3 of x. And when is this true? It's only true for x being between negative 3 and up to x equals 0. So I'm going to have to write that. Negative 3 can equal that, or up to 0, and including 0. Notice I didn't say x is greater than negative infinity, because there's a solid dot there, so that means it must only be starting on the left at negative 3. So be careful. If you see a solid dot, don't think about going to the left of that dot. Okay, now we're going to talk about the line on the right. So the line on the right has a positive slope, and the slope is 3 over 1. So it's basically going to have this equation. mx, there's no b, b is 0, so it's going to be 3x. And when does this happen? This happens if x is greater than 0, or if x goes up to 1, or equals 1. Okay, So that's the answer to this question. We wrote down the function that best describes this graph. Now, it wasn't asked, but if we were asked to write down the domain, you would need to say this, that the domain is going from x equals -3 up to x equals 1. If we were asked about the range, I'd want to hear you say this, that's the y values, and I'd want you to write that it's going from y equals 0 up to 3. Okay, those weren't asked, but I'm just throwing it in there just for practice. Let's do the last example. Assume it costs 25 cents to mail a letter weighing 1 ounce or less, and then 20 cents for each additional ounce or fraction of an ounce. Let L of x be the cost of mailing a letter weighing x ounces. Graph y equals L of x, the cost of mailing a letter of any weight. Okay, so let's take a look. It can't be choice B, because choice B is saying this, that look at this, these are the ounces. If you have a 1 ounce letter, it's already above 25 cents. It's only letting you be 25 cents if you weigh nothing. But we know that it said if you're up to 1 ounce, it's 25 cents. And then it goes up in steps after that. You add an ounce, and then you have to add 20 cents to it. So this was 25 cents, and then say it's gone up to 2 ounces, then it's going to be 45 cents, and so on. So it's choice A. So that's a use of piecewise defined functions when things go up in steps, for example. Okay, that's it for this, and that's actually the end of section 3.4. It's really important that you know the library of functions decently, because it can make the problems go a bit faster for you. Okay, so good luck.